Okay, hello everybody. My name is Ali Reza Taheri, and I'm a second-year PhD student at the School of Computer Science and Cyber Sciences at Augusta University. And today I'll be presenting my research about side channel attacks on keyboard. And this is a project by my supervisor, Dr. Raza Rahaimer, and me. We all know that in today's digital age, safeguarding sensitive data is more critical than ever. And with the increasing use of digital devices, online communication, and AI, it is crucial to consider protecting our sensitive information. And within a security and privacy communities, electronic device emissions have long been a concern as they are susceptible to side channel attacks. But what is a side channel attack? Do you have any idea? Okay, here is the definition. The process of gaining knowledge about a system by analyzing its unintentionally produced signals or its side effects is known as side channel attacks. For example, when we use acoustic signals or acoustic noises produced by a device to attack that device, this is called acoustic side channel attacks. And they can pose significant threats to digital security by extracting sensitive information such as emails, passwords, credit card details, and so on. As I said, our research is about doing this kind of attack on keyboards. And one of the most concerning aspects of these attacks is that they can be conducted remotely without requiring any physical access to the victim's devices, and this makes them particularly appealing to cyber criminals who can easily target any kind of users. Also, this type of attack can be hazardous as it can bypass traditional security measures like passwords or encryption. Usually, a significant challenge in the existing attacks is precisely capturing keystroke sounds. And researchers typically address this challenge using high-quality microphone and limiting environmental conditions and noises. They also usually force the users to have specific typing patterns. However, in this research, we try to cover their weaknesses and their limitations by considering that user's typing pattern and also without limiting the users to have specific typing pattern or having a specific keyboard type. Also, we consider the noise in the environment. And we achieve a success rate about 43%, which I will discuss more about it. As a literature review, we classified the existing attack strategies into these three categories: timing-based, geometry-based, and frequency-based attacks. And if you are interested to know more about them, you are very welcome to take a look at our survey entitled Survey on Acoustic Side Channel Attacks. Also, Garcia et al. Worked on evaluating the practicality of acoustic side channel attacks on modern keyboards, and Yen et al. Have a paper on improved techniques for acoustic side channel attacks on keyboards. Also, before them, Shah et al. Worked on keyboard acoustic side channel attacks and exploring realistic and effective threats, which you can also find more detail about these attacks on this paper as well. However, an important thing is that our other approaches often overlook typing pattern, which I mentioned, which negatively affects their result. But our research turned this negative point to the positive one. Since we observed that the time interval between pressing keys on a keyboard varies from different key pairs, and also we noticed that each user tends to type specific key pairs within a similar time interval in most cases, and it relates to arrangement of keys on a keyboard, the anatomy of their hand, and personal typing style, which we consider all these three factors as typing patterns. For example, we observed that a selected user tended to type letters, for example, B and O, within a similar time in different words, such as words book or both. However, this time interval may vary from this user to another one. So we have to train a specific model for each user to attack them. Okay, but how do we define our threat model to be applicable in a real world? We actually try to keep our proposed methods simple and applicable to a realistic scenario. For example, let's assume a victim with a high-level sensitive job position is working in their office, and an attacker enters to the office under the guise of a client and make a dummy request that requires victim to send a response via email. Now, the attacker can leave a small recorder, a sound recorder in the victim's office, and the attacker can receive the victim's email after a while. Then, a couple of days later, the attacker can return to the victim's office again with an excuse and retrieve the recorders. So now, the attacker has the sample of the victim's typing text based on the email that he received, and also the recorded noise of his office during these days, that he recorded during these days. Please note that this is just a simple example. An attacker can use many other complicated methods to attack their targets, like using parabolic microphone or recording typing noises during online calls or meetings. To test our assumption, we developed an application that can capture a user typing pattern in 3 steps. First, at the left, the user types any desired text on their wish. Second, some common sentences in English are shown to the user, and the user needs to type them. Finally, at the third step, as the test data set, they should type a set of predetermined, commonly used words to capture a diverse range of typing styles and patterns. We chose these sentences and words based on the diversity needed to type letters and words in English. So now, using this software, we have our data set. What is the next step? The next step is to train a statistical model using the data set gathered from the user's typing pattern. In the first step, we calculated and stored the time interval between 2 pressed keys in a database table. Next, we calculated the average and standard deviation of this time interval for each sequence of similar keys and stored them in another table which serves as the trained model's data. Now, what is the input and output of our model? So quickly, we can give the model the time intervals that we can find them through processing or signal processing on recorded acoustic signal of unknown recorded keystrokes, and the model will predict some possible key pairs as its output. But how we can calculate time interval through the recorded noise of unknown keystrokes? As you can see in this figure, we have a chain of recorded waveforms related to each type keystrokes. This is 4 letters in a word. And we can systematically search for the maximum points because they are related to the touch and pressing time of the keys, and they are almost at the beginning of the keystroke signals. So we can calculate the time interval between these maximum points as the input of our trained model and get a bunch of raw prediction from the model. Now, we need to process these potential predicted key pairs to find meaningful typed words and sentences. For that, we developed a decision tree-like diagram to find the connection between letters and filter meaningful words. This diagram enables us to trace all branches connected through the root to the final branch, and also we can prune all remaining disconnected roots. as false results. In the next step, we can put all connected branch, let's say letters, together as potential words and filter the meaningful word, and we can do it again to find the meaningful sentences that the victim type. Also, we can use LLMs to find the sentences based on the context. This algorithm formulates the process of finding type keystroke that I just mentioned. Sorry. In the following slides, I will explain our experimental setup and results. And for our user study, we carefully selected 20 adults with different typing patterns and trained unique model for each user to evaluate our proposed methods. To do our experiment, we chose our test data set for its prevalence in English text and varied word lengths. This selection allowed us to measure the impact of word lengths on prediction accuracy. This figure shows that it shows the effect of the number of letters in a word on the accuracy. The chart indicates that the success rate increases as the number of letters increase until we reach 6 letters. And this is because having more letters create a larger tree. However, a larger tree doesn't mean necessarily result to having more meaningful words. And we achieved the highest rate after number 6. To measure the overall accuracy of the proposed attack, we conducted a series of experiments. In this figure, you can see the computed average number of correct detections per user and the total accuracy of our approach across all users in the red line. And you can compare them. Also, our investigation reveals a linear relationship between the average standard deviation of each user typing sample and the prediction success rate. This implies that users with consistent typing patterns tend to have a lower standard deviation, resulting in a higher prediction success rate. For instance, user number 7 exhibits the lowest ASD and consequently the highest success rate. Our findings prove our initial hypothesis regarding the correlation between typing patterns and vulnerability to this type of attacks. Additionally, our average success rate across all users is approximately 43% in a realistic environment, considering environmental noises, not limiting users to have a special unnatural typing patterns or using a special keyboard. Also, we used the laptop's built-in microphone, and it is important to mention that we can definitely improve our result using high-quality microphones. Comparing our result with other approaches is challenging, as they often constrain various parameters in their experiments to showcase the success rate of their methods. However, as you can see in this table, we compare some of our features and achievements to similar approaches, and our method outperformed others that just focused on predicting words. Also, our proposed method doesn't require a large data set, and it excels in considering user typing patterns, environmental noise, and without computational complexity like deep learning models, and it achieves a good success rate in detecting words in realistic scenarios. About the limitation, it is important to note that the strength of the sound generated by the keyboard is a critical factor in all acoustic keystroke detection methods. So if we cannot accurately capture the sound of the keyboard, definitely we may be able to identify them precisely, which result in the lower accuracy. For instance, keyboard with soft keys produce usually less sound power, which can substantially impact the accuracy of the final detection. We also have some difficulties with infrequent computer users because they usually don't have a a special typing pattern, and also with professional typists whose typing pattern are very fast and hard to detect. In conclusion, we have explored the possibility of acoustic side channel attacks on keyboards that are based on the user's typing pattern, and this approach provides a more realistic method that can be used against criminals and terrorist groups. As you can imagine, our project has significant military approaches and can contribute to national security. So we are seeking collaboration and funding support from all kinds of partners, including military partners, to improve and extend the project. And that's it. Thank you so much. Feel free to ask any question if you have. Any question? Yeah. Say it again. Sorry, I couldn't hear you. We explored that, and also we have another experiments to use different type of keyboards to measure the differences between them. But our results show that if we train another model based on that specific keyboard, we can achieve good results as well. Yeah. Yeah, please.
Yes. What about typists that make corrections? Are they able to detect the correction?
The backspace.
Backspace, or like they differentiate with the mouse?
To be honest, we didn't consider that, but somehow we can detect that, but it's a little bit hard, and we didn't consider that this research. Yeah.
When you were presenting last year, you only used the time interval between the keystrokes. Are you using a full waveform of keystrokes this year?
No. But in the other research, we tried to combine this research with them to improve the results considering typing patterns by this research, and also detecting the pressed keys by the other approaches like deep learning methods.
Do you have any plans on using the entire sound pattern of a keystroke waveform?
Definitely we have, yeah.
But I do that last year.
Yeah. Any other questions? Yeah.
And like a white noise generator or something like that, how do you like the section like that?
Yeah, why not? Yeah, we can do that.
Have you thought about putting a bandpass filter on the sound so that you only get the exact sound of the keyboard, filtering everything out?
It is really depend the environment that we are capturing the sound, because we don't know anything about the sound that are in the, for example, office that we are recording. But yeah, definitely we can use any kind of filters to capture better sounds of keystrokes. Yeah.
Would it help if you have a larger sample size?
No. We don't need to have that. And these experiments was just by recording about 15 minutes of typing of users, not more. Yeah. Others? Thank you so much.